All right, so continuing with lesson 5 with average rates of change and instantaneous rates of change. That's what we've been talking about in that last video. When we were finding average rates of change, we were finding the slope of a secant line between 2 points. I want to put this in a little bit different perspective. And let's just say that we have the growth of a fruit fly population in a controlled experiment. So the graph that is in blue represents the number of flies in this population on any given day. So let's say, and we're going to say, let's use the points 23, 150, and 45, 340 to find the average rate of change of the slope of the secant line that goes through those 2 points. And then I want us to talk about what does that value or slope mean. So here we have a point, 23, 150, and then here's our point Q, 45, 340, and here is the line, the secant line that goes through those 2 points. So really what we're doing is we're finding the slope of this line right here. Okay? All right, so to do that, the ARC is going to be the change delta P. We call this P for population, T for time, so it's the change in population divided by the change in time. That will give us the rate. It will give us a rate. And then we'll talk, once we find that value, we'll talk about what that rate represents, or that value represents. So here, okay, so we might want to do, I don't really have a function, I just have values. So this is going to be, what is the change in P? The change in P divided by the change in time. So I'm going to take the larger of the populations, 340. I will subtract the smaller of the populations. Now, let me ask, I want you to think about something. Why am I using those values? Why did I not use 45 and 23? Well, remember, your slope formula is change in y's over the change in x's, and in your ordered pairs, you have an x value and a y value, okay? All right, so 340 minus 150 divided by 45 minus 23. And so what that gives us, 340 minus 150, that's 90, and 45 minus 23 is 22. And I will pull my calculator out and calculate that. 90 divided by 22, is that right? Something doesn't look right. 90 divided by 22. Let me check my calculations, because that number does not look right. So 340 minus 150 is 190, not 22, not 90. I should have known that. So let me retry that. I knew something didn't look right. So 190 divided by 22, there we go. We get approximately 8.6363. Now let's talk about what that number represents. So the change in population divided by the change in time is 8.6363. Well, let's talk about the units. Your population represented the population of flies. So that's flies. Your time was in terms of days. So what this value gives us is the rate at which the fruit fly population is increasing on average between day 23 and 45. So the fruit fly population is increasing on average by 8.6 flies per day between T equals 23 and T equals 45. So between day 23 and 45, the number of fruit flies are increasing. The population is increasing on average by 8.6 flies per day, or you can round that up to 9 flies per day. So so again, if this is the slope, if that value 8.6363 whatever represents the slope of this secant line, if I want to find the speed, I've got speed on my mind. If I want to know the rate at which the population of fruit flies, and we'll take this away, if I want to know how fast the population was growing on day 23 itself, then I'm going to approach this the same way I did a few minutes ago, or in the previous lesson, not the lesson, but the previous video, when we wanted to find the rate at which the rock was falling at 2 seconds. So geometrically, I'm not going to spend a whole lot of time. I'm just going to kind of walk through this. We just found the slope of the secant line. We found that to be, and here's where that information is. That turned out to be 8.6. Some of this got cut off. Okay, then if we find the slope of the secant line between day 23 and 40, sorry, then that point is right here. Look at the secant line. Then we have a point at 35 day, or at day 35. So at day 40, the population, without going through and doing all the math, that turns out to be 10.6. Then if we calculate the slope of the secant line between day 23 and day 35, that turns out to be 13.3. And then if we calculate the slope of the secant line between day 30 or day 23 and 30, we end up with 16.4. Okay, so here's what I want you to look at. Here was the secant line. Between these 2 points, you had a secant line whose slope was approximately 8.6. Then we looked at the slope of the secant line between these 2 points. Then we found the slope of the secant line between these 2 points. Then we found the slope of the secant line between these 2 points. If we were to continue this process, let's talk about what's going on geometrically with the graph. Notice that the slopes of the secant lines are increasing. 8.6, 10.6, 16, 13.3, and so on. So the slopes of the secant lines are increasing. Let me pull that back down. Okay, then what is ultimately happening? We just did a few secant lines, but what if I kept pulling this point Q? What if I just kept moving it backwards and backwards and backwards? What would happen ultimately to that secant line? Well, ultimately, the secant line becomes a tangent line. And a tangent line is a line that touches a point in one place. So ultimately, your secant lines appear to become a tangent line. And therefore, the slope of the secant line would be the same as the slope of the tangent line. So as Q approaches P, as this point moves backwards along the curve, as Q approaches P, that means as T, time, approaches 23, then let's talk about the slope. The slope of PQ, which was the secant line, ultimately approaches the slope of this line AB. And this line AB is that point, or that line that is a tangent line and not a secant line. So again, we're using these words approaches. What does that mean? Well, what does that sound like? It sounds like limits. Okay, so in a population, so this was the geometric perspective. Let's talk about what the perspective, let's look at this from a real world perspective, the population perspective. Let's add some meaning to this. So as the average growth rates, the average growth rates are increasing for smaller and smaller time intervals, they approach the slope of the tangent line, and what that ultimately turns out to be is about 17.5 flies per day. So if I find the, let's say I'm going to use the points, point A is 15, 0. Point B, I've drawn all over this so it's hard to see. What is that, 35, 350? So these are the 2 points for AB, point A, point B. And calculating the slope or average rate of change between those two, that would be 350 minus 0 divided by 35, excuse me, minus 15, and that equals, what does that equal? That equals 350 divided by 20, which turns out to be 17.5. So this 17.5 is the slope of the tangent line, and it's that value that we would take as the rate at which the population is growing on day 15. So, no, on day 23, excuse me, because we're using this line for the point at day 23. So, the slope of the tangent line is going to be, I'll just write it. The slope of the tangent line which is 17.5, is the rate at which the population is changing or growing at day 23. So this average rate of change is closely related to limits. When we want to find a rate at which something is changing at a particular instant of time. Okay, so that kind of hopefully helps you to get a geometric visual perspective of slopes of secant lines becoming slopes, ultimately the slope of a tangent line. Let me bring this drawing back in. Okay, so I've drawn all over it again, but here we started with our 2 points, 2 and 2.1. Then we did 2.01. Then we did 2 and 2.001. As I move each point, as each point gets closer and closer to this point, that point ultimately, these secant lines ultimately become what appears to be a tangent line at the point 2. And so this 64 is the speed at which the rock is traveling at t = 2 seconds. For the fruit fly population, the secant line, we kept moving this point along the curve until ultimately the secant line becomes the tangent line, and the slope of that tangent line, 17.5, is the growth rate of the population of fruit flies at or on day = 23, or day 23. So finding a rate at a particular time involves limits, because as one thing happens, it causes something else to happen. So as the secant line approaches the tangent line, the value of the secant lines approach the value of the slope of the tangent line.